Hello, myself Dr. D.K.Shedge, Professor in Electronics and Telecommunication Department, AISSMS Institute of Information Technology, Pune. Today we'll discuss about the instrumentation amplifier. As the name indicates, instrumentation amplifier is used mainly in measurement and control of the low-level signals. So its main function is to amplify the low-level output signal, which is output of commonly a transducer, so that it can drive or it can be further used to control the action. The instrumentation amplifier thus is used for precise low-level signal amplification where it is desired to have the very low noise, low thermal drift, and the input resistance of instrumentation amplifier should be very high in order not to load the quantity under test and measurement. Besides these, the desired characteristics of instrumentation amplifier are it must have very low power consumption, it must have very high common mode rejection ratio, that is a CMRR, and it should have very high slew rate. Common mode rejection ratio is an indication of how effectively your amplifier will be able to measure the difference between the two isolated voltages in presence of the strong common mode noise. The requirements of typical instrumentation amplifier thus can be listed as it should be able to amplify the differential input, that is the differential input arrangement. Secondly, it should give us the single-ended output. It should have adjustable gain. Its input resistance should be very high. Its amplification facility of instrumentation amplifier in presence of common mode noise, it should be very high, that is a high CMRR. It should have a high slew rate so that it will be able to respond very quickly to changes in the input. It should have very low power dissipation, and it should have a very low offset voltage and thermal drift. This is the typical circuit diagram of the instrumentation amplifier. Actually, the second stage of the instrumentation amplifier, that is A3 along with RF and R2, the two combinations of RF and R2, this is nothing but our common difference amplifier or differential amplifier. This also can amplify the difference between two input voltages, but only thing in for one input it will be acting as a inverting, and for other input it will be acting as a non-inverting configuration. So it won't be able to offer very high input resistance for both the inputs. It will offer no doubt very high input resistance for the non-inverting configuration, that is the input which is coming at the non-inverting input terminal, whereas it will be able to give very low input resistance for the input which is coming at the inverting input terminal. Hence, it is preceded by the two non-inverting configurations. Here, these two non-inverting configurations are connected with R1, two feedback registers R1 to each A1 and A2, and one variable register in order to make a variable gain of the instrumentation amplifier. This instrumentation amplifier can be analyzed very easily. Let us assume that V2 is more than V1, and then we'll say that current flows from V2 to V1. Due to virtual ground concept, the differential voltage will be 0. Thus, voltage at this terminal will be V2. Voltage at this terminal will be V1. Thus, current flowing through resistance of R can be given by V2 minus V1 into R. The voltage between two inputs, 2 points, V4 and V3, can be given as V4 minus V3. The potential drop, we assume that V2 is greater than V1, that's why V4 minus V3, that is nothing but drop across R1 plus drop across R plus drop across this R1. So it can be written as I into R1 plus I into R plus I into R1. Drop across this R1 plus drop across this R plus drop across this R1. Here we assume that input currents to both the operational amplifiers are very low. Indeed, these are very low. These input currents of operational amplifier are very low. So V4 minus V3 can be simply given by I multiplied by twice R1 plus R, which will be given if we substitute for I in terms of V2 and V1, V2 minus V1 upon R multiplied by twice R1 plus R. The op-amp A3 just now seen, it works as a simple differential amplifier and its output will be given by RF upon R2 multiplied by non-inverting input minus inverting input, that is a V4 minus V3. For V4 minus V3 we can substitute here the formula. So RF divided by R2 multiplied by twice R1 plus R, but this R will be dividing to that term, hence we can write this as a 1 plus twice R1 upon R and multiplied by V2 minus V1. So here we see that output voltage is proportional to V2 minus V1, which is the difference between two input voltages, and the gain is given by RF divided by R2 multiplied by 1 plus twice R1 upon R. So R1 we can fix and R we can keep variable in order to have the variable gain of the instrumentation amplifier. Here in this case both the inputs will be experiencing the non-inverting input terminal of operational amplifiers A1 and A2, thus will be experiencing very high input resistance. So both the inputs will experience very high input resistance and also will get the variable voltage gain. Thank you.